Okay, algebra. We are doing section 3.6 today, and this is the last section of the chapter. We should be able to do the whole lesson today, I'm thinking. It shouldn't take too terribly long. There's only 4 examples, but they are a little bit longer. So this section is kind of the reverse of what we've been building toward this whole chapter. We've talked about it, quite a few things, like just in the last section, like line symmetry. We talked about, let's see, in the section before that, we talked about X and Y intercepts. We talked about increasing and decreasing function. Let's see, or increasing and decreasing sections of a graph, I guess I should say. We talked about those things. We talked about, maximums and minimums. Okay, I think that mostly is the main idea. Intercepts, a domain and range. We talked about end behavior. Domain and range. So all of those things. But in the last sections, the difference is in the last sections, they would give us a graph like this, and they would say, tell me all of these things. Now, the only difference is they're going to be telling you these things and saying, make me a graph, right? And that's just the main difference. That's about all there is to it, okay? So they have here sketching graphs of functions. It says you can sketch the graph of a function using key features knowing the domain, range, intercepts, symmetry, end behavior, extrema, increasing, decreasing, positive, negative, we should add to that list. Positive and negative, those things all can tell me what graphs are. So it says label the graph to identify its key features. This little dot right here is going to be a relative maximum. That means this guy down here is a relative minimum. I think what they're getting at in this little blank is that this function is increasing here. So increasing, I'm just going to put INC. Here the function from here to here is decreasing, and here the function is increasing again from there to there, okay? So we've got kind of like just different things chunked off from the graph, okay? So let's see an example of where they have some things and they want us to sketch a graph. So this, they say, is a linear function. So example 1 has to do with linear functions. So on your homework assignment, when you get to that, pay attention to which ones go with which examples, because that might help you determine whether it's a linear function or not. Remember, a linear function looks like a line. So in cycling, in this 2015, Christoph Strasser set a new 24-hour cycling record. So he's been on the bike for 24 hours, and he goes 556 miles in 24 hours. I wouldn't be able to function after 24 hours without sleep, let alone being on a bike the whole time. The distance he rode over 24 hours can be represented by a function. Sketch the graph. So one thing that they did was they took all that information and they said, okay, let's put it into like a kind of a summary right here. So they said the y-intercept, okay, if we have this going on, we have time down here, okay, all from 0 hours all the way up to 24 hours, and then this is the distance that he traveled. Well, they start with like the y-intercept because they're saying at a time of 0, he will have traveled 0 miles, right? Okay, and really, all of this information is here, but sometimes you don't need all of that information in order to be able to graph what this thing looks like. For example, I know that this is going to be a linear function, and he starts at a time of 0, he has gone a distance of 0, and a time of 24, he's gone a distance of 556? 556, so about like there, right? And if this is a linear function, I just draw a straight line from there to there and then I'm done, right? I didn't even read the rest of this stuff, okay? So I started with the y-intercept, I went to 554, but let's make sure that all of this other stuff is true as well. Is it linear or not linear? It is a linear function because as time goes on, the distance traveled is going to go like that. Now, this is assuming that he is going the same pace each hour, right? So like the slope is going to be the same. That would reflect the same pace every hour, right? So maybe there were some hours that he wasn't going as fast as other hours, and that would kind of be, a little bit like something like this as he's climbing up, right? But they went ahead and said, no, let's just assume that he's going the same pace every hour. So it looks like that. It is positive for all times that are greater than 0. Positive means it's above water, right? Above the x-axis, which would make sense. It is increasing for all times that are greater than 0. The end behavior, as x increases, the y increases. So this is just a graph of what he looks like, right? That's just the graph of the described scenario that we have up above there, okay? Let's do number 2, sketch a graph of a symmetric function, okay? Now, linear functions don't have symmetry, like they don't have a line of symmetry you're reflected across. So I'm going to guess that this is probably not a linear function. Let's see what we've got going on here, though. It says a person's happiness can be affected by temperature. I believe that. I think I'm more happy in the summertime probably than I am in the wintertime, at least about the weather. Sketch a non-linear graph that shows the happiness of a person. Okay, so what we've got going on here is we have that it's positive between 25 and 89 degrees Fahrenheit. Let me go down to my graph. I think it's on the next page, sorry. Between 25 and 89 degrees Fahrenheit, it is positive. 25 and 89? 25 and 89. Okay, 25 is about here. 89 degrees is about here. Okay, and it's positive. So I'm guessing that like we're above water. Maybe he's a parabola that looks like that. Okay. So that's kind of what I'm guesstimating is happening. Okay. Then let's see, what else do I have that I can use? Some of these, so he's negative when he's less than 25 and he's negative when he's greater than 89, right? So he's down below here and here. Okay, I'm guessing this is going to look like a parabola. I already kind of have an idea of what this looks like, but let's do some more. For temperatures that are less than about 57, it's increasing, and when it's greater than 57, it's decreasing. Okay, all right, so 57 is about right here. And that's going to be like kind of my maximum, right? It's increasing till I get to that point, and then it's decreasing after that. Okay, so yeah, this is pretty well. It's going to look like a parabola. Let's see, and then they have some end behavior. They have relative maximum, so at about 57 is where the happiness is at its peak. 57 degrees. I don't know. That's a little too cold for me. I think 57 would not be my peak happiness. I think it would maybe be like 75. 75 is peak happiness for me, probably, but whatever. I don't know. End behavior, as temperature increases or decreases, a person's happiness decreases. So they're saying basically on either side, it doesn't matter. If the temperature gets too high, you're going to be unhappy. If your temperature gets too low, you're going to be unhappy because it's down on either side. So the degree of your happiness is indicated with temperature. So that's kind of an interesting graph, but it has those qualities on there. Again, you don't need probably every single one of these before you have an idea of what the graph looks like, right? You're just kind of putting those pieces together. A lot of times your graph will end up developing after only like 2 pieces of information, right? Okay, oh, and then we didn't even look at symmetry. A person's happiness for temperature less than 57 is the same as their happiness for greater than 57. Okay. All right, let's do the check real quick because they have correct or incorrect. So we have this graph here, and it's uses key features to sketch the graph. They want to figure out whether this is correct or incorrect. So is the graph positive or above water between -3 and 0? -3 is here, 0 is here. Is he positive between those two? Yes. And when he's greater than 2? Greater than 2, yep, that is correct. Okay. Is it negative when it's less than -3? Now, -3 is right here. When it's less than -3, which means on this side of -3, is he negative and between 0 and 2? Yep, he's below water there, so that is correct as well. Is he increasing? Let me get rid of my marks here now. Okay. Is my function increasing when x is less than -2? -2 is here, right here. Okay, so on my graph, they're saying about right there. When he is on this side of that dot, he is increasing, right? From left to right, he's going to be going uphill, okay? And he's increasing between 1 and 3, right? From here to here, okay? Yeah, that's kind of true. Yeah, I mean, he will continue to increase up there as well, but whatever, that's fine. We'll say that that's correct. Is he decreasing between -2 and 1, and when x is greater than 3, is he decreasing? Well, maybe if he turns around and goes back, that he is decreasing from here to here, but we don't necessarily know that he's decreasing on this side, so this part of it is not necessarily true. So I'm going to say that that's incorrect for decreasing. Okay. Intercepts. Erase all my stuff again. Intercepts. Does he have an x intercept the x-axis at -3, 0, 0, 0, and 2, 0? -3, 0, 0, 0, 2, 0. Yes, that is correct. Okay. Does he have a minimum at 1, -2? 1, -2, is that about where the minimum is? Yes, that is correct. Okay. Does he have a maximum at -2, 4? About there? And does he have also a maximum at 3, 2? 1, 2, 3, 2. That's not right. So this one, he has a relative maximum. That is incorrect. As x increases and decreases, the value of y decreases. So as x goes this way, he's decreasing. As x goes this way, he's decreasing. Well, here he's increasing. So that one is not correct either. Okay. So just different things that we can pick apart of a graph, and you know, they all come together to form what it looks like. All right, let's go to example 3. This is another non-linear graph. So the number of people in line for a roller coaster throughout the day can be modeled by a function. Use the key features to sketch a graph of the function, then interpret the key features. Okay, so it's positive. Actually, you know what? Here's what I'm going to do. Instead of starting with positive, negative, I'm going to start down here where we have relative max and relative min. I'm going to do that. Okay, so my minimum is at 5.3. Okay, 5 is right here, so 5.3 is maybe about there, and 133. Okay, this would be like 150. So 133 would be like right there-ish. Okay, so there is a minimum right here. Min. I'm just going to like label him. Okay, then we have 2 maximums. One of them is at 1.4, so like here, and 448, which is about right there. That's a max point. Okay, and at 9.9, which is here, and 643. 643 would be almost 650. So right here, this is another maximum point. Okay, all right, so he's kind of probably do one of these, right, in between those. Let's see what he's doing on either side of that. Okay, so relative max, relative min, check. As the x increases or decreases, the value of y decreases. Ooh, so that means that he's decreasing for y on both sides. So here and here he's going to be decreasing, something like that. All right, but let's read a couple more things before we definitively say that. The intercepts, the graph intersects the x-axis at -0.5, 0, so he touches there, at 12, 0, which is there, and intersects the y-axis at 0, 220. Okay, so now I have what my graph looks like. Right here, something like that, and something like this. Okay, now the number of people is what the y-axis is. We would not put arrows that go down here because that would say that we could have like a negative number of people. So we don't have arrows that go like that. We just are going to have them stop and do little dots on either end. Okay, so we could go through and check these off and make sure he's positive between -0.5 and 12. -0.5 and 12, he is above water that whole time, right? He is negative. They do say it's -4 here and here. So it does go below. I don't believe that. I don't like that they put that in there just because that would represent a negative number of people and you can't have that. So I'm not happy that they put that on there. That I don't agree with. He's increasing on this side of -1.4. So he's increasing from here to here. And between 5.3, which is here, and 9.9. So that's where he's increasing. Then he turns around and he's decreasing on the other parts of that, right? Okay, so decreasing. And then we've already done the intercepts. So this is what my graph is going to look like, something of that nature. Again, I did those out of order, right? I went with my maxes and mins first and then did the intercepts, and it kind of gave me a better idea of what this thing looks like, okay? So you don't always have to go in order. You don't always have to look at all of the pieces of information. I would still check them over after you've graphed your function just to make sure that it checks out. But sometimes you can put the pieces together without even looking at all of the information. Okay. All right, let's do the last one. Example 4. It says Hawk I is a computer system used in tennis to track the path of the ball. It is used as an officiating aid to locate the landing spot of a tennis ball when players challenge a call. Use the description of the player's forehand and backhand shots. Okay, so here's the deal. We're looking at forehand shot and backhand shot. Like one of them is like as you're going forward, and one of them's, like a forward, a backhand shot, in tennis. Okay. But the problem is to compare them, I have to try to compare these two, but one of them's written in words and one of them's like written on a graph. So here's what I'm going to do. I'm going to take this information and I'm going to try to like graph it on here so that I have like that double graphed. Okay. So during the forehand, the ball leaves the player's racket at a height of 2.8 feet. Okay, 2.8 is going to be like right about there, so maybe about the same spot. Okay, it travels 29 feet when it reaches a height of about 10 feet. Okay, so 10 feet and 29 is going to be about here. So it's going to go like this. All right. So it goes up. So if you're going forehand, evidently the ball reaches a lot higher than if you're going backhand. Okay. Then the height of the ball decreases until it hits the ground 58 feet from where it was hit. Okay. 58 feet is going to be about here. So this is what my graph is going to look like. Okay. So the forehand evidently has a higher distance up in the air, but it doesn't go as far lengthwise, versus backhand goes a little bit further out. It's kind of more of a short, long hit, okay? So that's kind of how we can compare those two. So I need to kind of put them in the same units. This was in words, this was in a graph. So I'm going to put them both into a graph so that I can compare them, right? And now we have this information that we can draw. So the y-intercept for the forehand was 58. The other one was 70, right? 58 versus 70. This one is 2.8 versus 2.5. That's about the same spot, right? For the y-intercept, okay? The extrema, the height for a forehand was 10 versus 7 feet for backhand. So it doesn't go as high for the backhand one. It's increasing and then it's decreasing and all of that stuff. Hi. Okay, let's fill in these blanks real quick. The tennis ball travels 12 feet farther during the backhand shot, right? The distance here, 12 feet further for the backhand shot. So backhand. Let's see, the y-intercept here, right here is my y-intercept. That's what they're having to compare second. The y-intercept of the two functions mean that the tennis ball is about 0.3 feet higher at the beginning of the forehand shot, which is this orange one. Okay, so it's a little bit higher for a forehand shot than a backhand shot. So forehand. Okay, the extrema, the maximum height of the tennis ball, is 3 feet higher during the forehand shot. It's 3 feet higher. Forehand. Okay, and then increasing, decreasing, the height of the tennis ball increases over a blank interval during the forehand shot, but it reaches a blank maximum height. So the forehand shot, it reaches a this means that the tennis ball is increasing at a blank rate during the forehand. The height of the tennis ball increases over a, I bet you they want to say short interval. The height of the tennis ball increases. This is a shorter interval than it is from here to here. So that's why it's going up higher really fast. A short interval during the forehand shot, but it reaches a high maximum height. It's a higher maximum height than the backhand shot. I don't know if these are the correct words, but we have the general idea. This means that the tennis ball increases at a faster rate. Faster rate, right? So like here, this is increasing at a faster rate than it is here because we have higher to go up in the air, okay? Again, I don't know if those were exactly the right words, but that's the general idea, okay? So again, you're just using this information to either graph functions or pull information from these, and that is it. Do 1 through 6 all. Okay, so front page, back page, again, some of these just start with one piece of information. If one piece, like let's say you start with the x-intercept, they say that there's none. Well, that didn't tell me anything, right? So maybe skip around if you want to start in the middle and use a different piece of information first to help you graph it. That is okay, like totally fine. You can skip around, and a lot of times you will end up graphing what these look like before you even get through all of the pieces of information, okay? All right, happy Friday. Do a good job. Help each other if you need to. There you go.